everyone, it's me, Carolyn, and in this video we are going to take a little switch to looking at things a little different than what we've seen so far, and we're going to be looking at proportions. Now, thinking of proportions, it will have a feel of like a binomial at times, because when you're thinking of a proportion, you're thinking how many people do a certain thing out of however many. And a lot of times it's will be these people do it and these people don't kind of thing. So that's very, very similar to a binomial. However, we're going to be looking at not a binomial because we're going to be just looking at these numbers. We won't have like what's the probability of exactly five of them doing something. We're going to be looking at things a little bit differently. So what we're going to do is just get used to the terminology first of all, and some of the symbols that go into it, and then we'll go from there. So first of all, let's just do an example. And we had that one pre-election poll finds that 53% of the 1,096 likely voters favor candidate A. A different poll found that 48% of the 756 voters favor this candidate. Now, both the 48 and that 53% are estimates for the true number of people that favor this candidate, just based on different polls. So some of the notation we're going to be seeing is we will use just the regular P for our population proportion. Sometimes there is a Greek letter that goes with this, and for the life of me today, I can't think of it. But we'll just call it P is our population proportion. And then we have P hat, because there's a little bitty hat on top. We've seen S hat before. And P hat is our sample proportion. So both the 53% and the 48%, which we could write as decimal form. And a lot of times it is done, things are done in decimal form as opposed to percentage form when we see them in formulas. And but those are two different P hats. Sometimes you actually need to find what P hat is, so that decimal we need. So sometimes remembering that is going to be the number of successes in our sample over N, and that will be our P hat. It turns out, and I do not go through what, where, or why, or how, but if you want to take other statistical courses that go into the theory behind all of this, that's where you can learn why the mean of P hat is actually P, and that our standard error or standard deviation of this P hat is the square root of P times 1 minus P all over N. Now, remembering that N does stand for our sample size and P is our population proportion in decimal form. Further, if N is large enough, we will have a normal curve. So that's another nice thing we'll see is it will be a normal curve, not like a T, the normal curve. So we can go back to our normal curve and work with that. A conservative rule, meaning that we can probably get by with something smaller, but just be conservative. If both N times P and N times 1 minus P is bigger than 10, again, P being in decimal form, it will be that normal curve. So let's just kind of get a feel for what all this means. So let's suppose there's a 25% chance that a home in the US will be affected by a high level radon. A random sample of 150 homes were chosen and found that 30% of the homes are affected by radon. So first of all, what is the mean of this distribution? Well, the mean of this distribution is actually P. Okay, and so we need to find the P, not the P hat, in this situation. So the P is that 25% or the 0.25. Now this 30% that we found, that was in our sample. So this is actually P hat or 0.3 if you want to think of it that way. And that was the answer to the next question. What is the estimate for this distribution? Well, that's p hat, which is that 30% or the 0.30. Okay. What is the standard deviation or the standard error? That is going to be our square root of p, 1 minus p, all over n. Or our p is 0.25. 1 minus 0.25, and our n was 150. Square root 0.25, 0.75 over 150. And I can go to my calculator to get this value. I do have to be a little bit careful when I'm doing this because I need to make sure everything is underneath that square root. And I come up with 0.0353, and I'm going to run out of room on my paper, but I have 55339. So there's a bunch of digits, but there are more. Okay. And then the shape, that's where we're going to check to make sure that n times p and n times 1 minus p are both bigger than or equal to 10. And if they are, we will be normal. So my n is at 150. My p was 0.25. My 150 times 0.75. And I had done 1 minus p before, so I just pulled that 0.75 from there. So 150 times 0.25 is 37.5. And 150 times 0.75 is 112.5. So notice both of those are bigger than 10. This situation is normally distributed. So we would be allowed to use a normal curve. Okay. So let's just continue. Since it was normal, let's ask ourselves some questions. What is the probability that the proportion is greater than 30%? So what is the probability that our P is going to be greater than 30%? Not that we needed our P hat. So this is when we don't really need that estimate in this situation, but we're just saying, oh, okay, at random, if I went and took a sample, what would be the probability that that proportion that of our sample is bigger than that 30%? And we can use SALT for this. So remembering it is now considered to be normal. So I do have a normal curve. And my mean is 0.25. And I want to know bigger than 30, so 0.30 and going bigger. And from before, just so I have it here on the page, the standard error, so that sigma of my P is 0.035. Should probably get some more digits here. 35. I wonder if I still have it on my calculator. I do. 35539. So I'll get some more digits for us. Okay, but we are going to go and use SALT, and we should be pretty good at this by now, because we have done the normal curve quite a bit. So again, the normal curve is under our distribution calculator. That's where we find probabilities. We do use the normal this time. Our mean is going to be that 25% or that 0.25. Our standard deviation is at 0.035355339. And I want a right tail. And we want to go bigger than 0.3. And we get a probability equal to 0.07865. Yeah, you will find that we're going to be doing a lot of things that we have done in the past. We're just going to be doing things a little different because the terminology has changed. So we're still using a normal curve. And that's the nice thing about proportions is it does follow the normal curve. We don't have to make sure that we know all certain pieces, and so on. I'm going to go back to our question. And actually what I'll do is I'll just read the question and I'll put the answers. We want to find the probability that the proportion is between 22% and 27%. So between 22% and 27%. So that means I want to do a between and bigger than 22, but smaller than 27. Okay, and we get an answer of 0.51612. So again, my mean hasn't changed. That standard deviation is that ugly square root piece with the p, 1 minus p all over n. And we get that value. So between 22% and 27% would be 0.51612. Okay, so there was the one we'd done started with. And here's this guy. I could have drawn a picture because we are doing 0.25 in the middle, 0.22 here, 0.27, and between. And that when I use salt, I got the 0.51612. Let's do another example here. Oops, lots of page here. A study finds that 18% of college athletes across the United States feel stressed in their studies due to lack of time management. A random sample of 60 athletes was taken. What is the probability that no more than 20 of them will be stressed due to the lack of time management skills? So I'm just going to kind of go through our pieces. Okay, this 18%, that's my P. That's my mean of the situation. My N, so I'll need that, is my sample size of 60. And we want to know what is the probability that no more than 20. Now notice we're not talking the same language here. We are talking percentages, so we're talking proportions. So we need to change that 20 also into a proportion. So that would be 20 out of the 60 that we talked about, which is 0.3333, and I don't know how many threes we want to add, but that's like 1/3. Okay, and we want to know what is the probability that our P, our proportion, is no more than, so that would be smaller than the 20 out of the 60. Making sure to keep our proportion talk similar. Okay, I do need to make sure that we can use the normal. So I do want to make sure that n times p and n times 1 minus p is bigger than 10. So my n times p and my n times 1 minus p, which is 60 times 0.82. Get both of those values here. 60 times 0.18 is 10.8. Ooh, not. And then the other one is 49.2. So both of those are bigger than 10, so it is normal. So I will be able to go to SALT and figure this out. If I wasn't able to go to SALT, I could do this one in terms of a proportion. I mean, a binomial, because this is a binomial type situation, provided all of our college athletes were independent from one another. And that is something we should have here as well. We want to make sure to take good samples when we're taking samples. And let's see, so I want to also get my standard deviation, which is that square root of my P times 1 minus P all over N. Because I'll need that in my standard normal, because we'll need the mean and we need our standard deviation. So 0.18 times 1 minus 0.18 all over 60. So 0.18 times our 0.82 all over 60. And a lot of times when things, when you're doing binomials for that matter, they will sometimes use proportions to approximate those values too, especially in the case if you had to do it by hand. Think about calculating this by hand, no more than 20. That means if you were doing it by hand, you'd be calculating the formula for 0, 1, 2, 3, 4, all the way up to 19, adding those all up, and then that way. Here, we can use the normal curve and go from this 0.33 down. And so hence the reason we do see this done a lot instead of the binomial. Okay, where was I? Calculating my standard deviation, 0.0495983887. Okay, and now I will go to SALT to actually do the work for me. We are using our normal curve because it is normal. Both our n times p and our n times 1 minus p were larger than 10. My p, which is my mean, is that 18% of all athletes feel stressed. The standard deviation was at square root of p times 1 minus p all over n, which was my point, oops, 0.04959837. Okay, and I wanted to do smaller than, so that would be a left tail. And 20 out of 60, which was 0.333, so I'll just do 0.3333, as many threes as I can. And we get that probability is 0.999. Pretty much a for sure thing. But if you think about this, the average is 18%, and we want to know what's the probability that we're less than 30%. So again, quite a bit larger than the mean. So we actually are the z-score is 3.09 standard deviations above the mean. So we do get 0.999 or 3 nines. And I put that right in here for us where that probability statement was. Okay. All right, let's do another one. Okay. Let's do another probability. So in a fairy tale statement, Jack and the Beanstalk, Jack sold family's 5 cows, or the cows, for 5 magic beans. We knew that the mother threw them into the yard after she found out what she did. If we knew that 90% of all magic beans sprout, suppose we randomly selected 100 magic beans. If all of them are planted, what is the probability that 95 of them will sprout? So we could do this for the 5 that Jack's mom threw out, but we'll do it for 100. We know that the probability is 90%, so our mean is at 0.9, 90%. Our n is the 100. If I take n times p, I get my 100 times 0.9, that's 90, and my n times 1 minus p, it's going to be my 100 times 1 minus 0.9, which is going to be 10. Both of them are bigger than or equal to 10, so it is going to be normal. So we can use the normal. And my standard deviation, because I'll need that as well, is my 0.9 times my 0.1, which I did up here when I calculated it, over 100. Okay, let me get my math here. 0.9, oops, square root first. Square root 0.9 times 0.1 divided by 100. 0.03. Okay, so we want to know what is the probability. So 0.9, that more than 95 of them will sprout. That's 95 out of the 100. I want to know what is the probability their proportion is going to be bigger than that 95 out of the 100. Or this is 0.95. So 0.95 is here. Probability that we're bigger. Okay. Looking at this 0.03, that's going to be quite a few standard deviations up because 0.95, because this would be oh, we'll see. We'll look at it. So we're going to go to salt. Well, and I'm going to set this next one up before I go to salt and get both of these answers at one time. And we're going to find the probability that less than 60 will sprout. So this is sometimes you won't be given a proportion of them or percentage, like what is the probability that 35% will sprout, but 60 out of the 100. So that would be probability that P is less than 60 out of the 100, or P is less than 0.6. So here's my 0.6, we want to go smaller, but the 0.9 is my middle. Okay, so we're going to be doing two problems in SALT, going bigger than 0.95 and going smaller than 0.6. But I'm going to go to SALT and do both of them. Okay, so we are using a normal. My mean is that 90%. My standard deviation, which is the square root of P times 1 minus P over 100, that was 0.03. That no rounding needed there. The first question, we wanted to know that more than 95 will sprout. So we want to go more than, so a right tail, and more than 0.95. That gives me 0.04779. We also wanted to do what is the probability that less than 60, so that's going to be a left tail, and less than 60 will sprout. Notice that that's a z-score of a -10, hence the reason not very likely that that's going to happen. And if you think about it, 90% is the chance that they will sprout, 90%. So, and on average, 90 out of those 100 would sprout. So the fact that we get less than 60, not very likely. So again, looking at our answers, sometimes you probably can get a feel for them before you even calculate them. But also when you get answers like zeros or numbers that are really large, like close to 1, you want to make sure that you double check that they make sense. So our first one was going bigger than 95. And with that 0.03, this would have been 93 and then 96. So it's between 1 and 2 standard deviations. So we will get some sort of answer. Going all the way down to 60, that's like it said in SALT, was 10 standard deviations below the mean. So going in that tail, we know that tail is very, very small. In fact, pretty darn close to 0. Okay, so that is kind of how we can calculate probabilities of a binomial type question using, instead of the binomial formula and the binomial distribution, we can use a normal curve. If we think of them in terms of percentages or decimals, instead of 20 out of the 60 and 95 out of the 100, and turn them into their proportions, we can calculate those probabilities. We can also do something similar to this if we want to try to estimate that true population proportion. So say we don't know P, but we want to try to get a handle on what it is. Again, most of our confidence intervals start with some sort of estimate, and then we go up and down a margin of error to calculate this. This one is very similar to that. The estimate we're going to use for P will be our P hat. So our sample proportion, that P hat is going to be our estimate. Our margin of error is always of the form, some sort of critical value based on the shape or the distribution of our variable, and then that standard error. Now, we don't have P, so we couldn't use P in our standard error. So we have to adjust it a little bit and use our P hat in here. It's nice thing is it'll still be normal, provided we get that n times P hat and n times 1 minus P hat to be bigger than 10. Some things you will start to notice when you're doing these things, if you take that P hat in terms of decimals, the n times the P and the n times the 1 minus P, those are like the number of successes and the number of failures. So we need the successes and our failures to be bigger than 10. Okay, and since it is a normal, we will see those Z stars show up as well. So we'll have our formula will look like our estimate plus or minus that Z star, P hat, 1 minus P hat all over N. We will be using salt for some of these, but I'm going to do the first one both ways, using the formula and to make sure we use salt as well. So we're going to find a 98% confidence interval of the true proportion of students who have outside jobs. So we went to a sample of 500 and we found that 420 of them have outside jobs. So our P hat is going to be that 420 out of the 500 students. Remember, it has to be a proportion, and we probably want to write that as a decimal. So we can think of it in terms of percentages if we want to. So like 84% of our students have an outside job. That's what our estimate is. So that's going to be the first part here. So I also need my Z star. Okay, so I'm going to put my formula in here. But I also want to make sure that I can use this because I want to make sure we have the normal curve. So I'm going to look at N times P hat and my N times 1 minus P hat, just making sure that they're bigger than 10. My N is that 500. And we found that P hat to be 0.84. Now, if I multiply those together, I get my 420. That is not a surprise because 420 is the number of successes that we had, which is exactly what N times P hat will be. I can calculate this. If I do 1 minus 84%, that's 16, so 0.16. If I multiply those together, I do get 80. Notice these two numbers do add up to the 500. Also, this would be the people who do not have outside jobs. But both of them are bigger than 10, so we can use my normal curve. All right, so my P hat is at 0.84. My Z star, which I will go back a couple of videos, find my table, or I'll go to some other place and I'll find my 98% confidence critical value and I get 2.33. So I pulled it off of my table from before. And now I'm going to put all my pieces in. So my P hat is my 0.84. My 1 minus P hat. And my N is my 500. Okay, I'm going to just clean this up just a little bit. So 0.84, multiply that by 0.16, divide that by 500. Okay, I'm going to calculate this piece that I need to add and subtract. So I'm going to take my square root, 0.84, times my 0.16 divided by the 500, all underneath my square root, get that number, and then multiply it by 2.33. And so I'm taking 0.84 and I'm adding and subtracting 0.0382, and then there's a couple zeros. So I'm just going to stop there. I'm going to add first of all, so that's going to give me 0.8782. I will also take 0.84 minus that value, which gives me 0.8018. So here is my lower bound, which we've seen calculating confidence intervals, and my upper bound. Okay. We can do this very quickly in Excel. I mean, not Excel, excuse me, in SALT. Very similar to the way we did it with our t distributions. So I'm going to go into SALT and kind of walk you through it again. Okay. We could do it here if we wanted to, doing a between, setting up our pieces here. That would require us to calculate this number and then putting our 0.998 into this spot. However, there's a much easier way to do it, and that is using our inferential statistics. And instead of doing a one sample t, they have a one sample proportion. So we took one sample proportion, the 420 out of the 500 students. So the number of successes, well, that was our 420. The number of trials, that was our 500. That's all you need to know is to calculate our confidence interval. You should check your n times p and your n times 1 minus p to make sure that they're bigger than 10 before you go and do this. Sometimes people just do it anyway, although we want to make sure that we're following the correct processes. All right, so we are going to find, that was our number of successes out of our number of trials. We are calculating a confidence interval, and we are doing a 98% confidence interval. So I just type in my number of successes out of the trials, get my 98% confidence interval, and generate my results. This does set it up a little bit different than the other one did, which is kind of nice because then you can kind of see that there is a different form. But you'll notice here we have that 0.0818 that I had before, and my 0.8782. Again, I did it by hand, but I had my standard error. I did not round. They rounded their standard error a little bit. Because I had left all of my digits in there, I have a little bit different standard error. So, or they may have used all the decimals and I truncated. Either case, we're pretty darn close. So 420 out of the 500 students, confidence interval 98%. The thing they might have done is that 2.33 that I used, they may have used more decimals in the Z star. So depending on what their Z star is, is probably the difference in these values from what I have. But notice it was accurate, pretty accurate to, well, accurate to 3 for sure with what we had done. SALT is going to be much more accurate than what I do using the formulas, mostly because I have been using critical values that have only got a few digits. They probably have critical values that use much more. Okay, we're going to go back to our document and we'll do another example. Okay, so we have researchers studied 2,000 prescriptions and found that 1,600 of them were not adjusted for weight. We want to construct a 95% confidence interval of the true proportion to adjust for that. Okay, so the first thing I need to do is find my p hat, find that point estimate, which is the 1,600 out of the 2,000. And if I calculate that as a decimal, I like to calculate it as a decimal. Not that I need to, because if you saw, remember, just in salt, all we needed to do was 116,000 out of the 2,000, 1,600 out of the 2,000 were the only pieces we needed, and then the 95%. I don't even really need to use it for this either, because the n times p is going to be the number of successes. In this case, this would be, I wouldn't consider that a success, but that's going to be that 1,600 would be here. The n times 1 minus p hat will be the number of failures, which would be everybody else. So those are both bigger than 10. I could have taken my 2,000 and multiplied it by the 0.8. You will see that that does in fact give you that 1,600, which is the number of successes. I could take the 2,000 times my 0.2, which is 1 minus p hat, 1 minus the 0.8, and that does give me 400. So again, either way you remember how to do that will work. But again, we're going to go to salt to find the confidence interval. And we could do it again two ways. We could go into the distribution calculator, and although doing the inferential statistics is much faster. Again, in the inferential statistics, we want to use the one sample proportion because we are talking about finding a true confidence interval for P. And in this problem, we had 1,600 out of the 2,000 people. We wanted to do a 95% confidence level interval. I'm going to hit my equal button. And my lower bound is 0.78247. My upper 0.81753. You'll notice there's that p hat that I did calculate just so to kind of double check. There would be the standard error, which is that square root piece, that square root of p times 1 minus p all over your n. That would give you this value here. Okay. Hopefully I'm not talking too fast for you. I think the computer sometimes slows me down a little bit. So here was our confidence interval. What this again tells me is if you were to interpret this confidence interval is that you are 95% confident that the true proportion of doctors who do not adjust for weight is somewhere between, I'm just going to round it to the nearest whole, 78% and 82%. You'll notice that our proportion, that P hat, is smack dab in the middle, which it should be, because remember we took our estimate and then we went down a little bit and up a little bit. So we start at that in the middle and then go down our margin of error in both directions. Okay. The last thing that we're going to talk about here is finding that sample size. We did it for when we were looking for a sample size, if we were looking for a true mean, both when we knew our standard deviation and when we didn't. Here we're going to do the same sort of thing that we would do before, is we start with that margin of error formula and we solve for n. So notice we're going to have to divide by our z, then we're going to square both sides and calculate for n. So this is the formula that we would get using some algebra, not that you need it, to find n. We do have a slight problem. No problems finding z stars. We've never had that. M would be given to you in the problem because M is the error that you're looking for. You have a confidence that you want to achieve. You have a margin of error that you want to achieve. The issue may be in whether or not we have a p hat. Because if this is some brand new experiment, we may not have p hats. Sometimes we can use old information as like historical evidence to use that as a p. However, we have done some calculus on this little formula. And if you use 0.5 for your p hat, it leads to the largest possible n that you could get. So if we have a p, we're going to use it. If we don't have one, we will use 0.5. That's just something that happens in calculus. And if you ever take a calculus class, you'll learn how to do that. And if you want to, come back to this formula and solve it for p to maximize your n. Okay, knowing that z star and m are just some numbers, constant values. All right, so here we're going to do a couple examples. So we have a new cheese product is being tested by giving out free samples to customers and asking whether they like it or not. They want to find a 98% confidence level, and they want to be within 0.03%. So they're like, okay, suppose they had a previous cheese and they found that 75% of those people liked it. So this would be something they could use as an estimate for p hat. So looking at n, our formula again is p hat times 1 minus p hat. Notice here, this is a little different than before. The only thing being squared is this portion. So we have to be a little bit careful when we're doing that. But now we're going to put our n pieces in. Our p hat is at 0.75. And then we're going to do 1 minus 0.75. Z star is going to come from our table for our 98%, and that is 2.33. And my margin of error, we want to be within 0.03 of the true value. So that's how far we're going up and down, is at 0.03, which is like 3%. So think of it that way. And now we drag out our calculator. So I'm going to first of all do a little bit of this beforehand, because that's going to be 0.25. And then I'm going to let up my calculator do all the work. All right, so I'm going to take that 2.33. I'm going to divide that by 0.03. I'm going to get that value first, and I'm going to square it. And I get that number. Then I multiply it by my 0.25 and my 0.75. And I came up with 1131.0208. Now we have to remember n stands for sample size, so we always round to a whole number, but we always want to round up, because if we round down, we are not necessarily going to get the accuracy that we're looking for, whether it be in the confidence or the margin of error. We won't quite do that. We're going to redo the same problem and say that there's no similar cheese product to estimate it. So that means I have no P's to work with. So that means we're going to use our standard value that gives us the biggest n possible. And that is n being, or p hat being 0.5. So we have 0.5, 1 minus 0.5, and then we're still going to have these same values. You will see that our n is going to get a little larger, make it a lot larger. 1 minus 0.5 is still 0.5. And you may see this formula a little different in textbooks because they will have multiplied that 0.5 times the 0.5 out and just have that number in front of it. So I'm going to start with my 2.33 again. I should have kept that in my calculator, but I didn't. Square that value. And we're going to multiply by 0.5 times 0.5, and I come up with 1,508.0277. So again, we round our n to a whole number and we always round up. And we get n to be 1509. Okay. Some people will ask, why don't we just automatically use the 0.5? I mean, if it's going to give us our largest n, why not just use it? Well, the reason is because every extra person you have to get into your sample is going to cost you more money. In this case, we're giving out cheese samples. So in this problem, if we had this to go by, we only have to give out 11,032 cheese samples. Okay. Now we have to pay someone to hand these out, or for mailing these out, we got to ship them to them. We have to get the responses back from all of these people. All of those extra things take time and money. So we want to try to keep n as small as possible, but we still want to make sure to get the n that gives us the results we want. Okay, we're going to do one last example of this, just to kind of talk about it. And I stole this example. I believe it's from our textbook as well. But we have researchers have found biochemical markers of cancer in exhaled breath of cancer patients. But however, the chemical analysis of these has not been proven effective as a way of diagnosing cancer. But we had this paper that was written in 2006. Feel free to go and read it. They described that sometimes we can train dogs because their sense of smell is so much better than our sense of smell. That possibly if we can train them to sniff our breath, and if they sense this, they can lie down. And if they don't sense it, they'll stay standing. So if we can do that, maybe we can detect cancer faster, because all we'd have to do is breathe on a trained dog. Anyway, so what we're going to do is we're going to try to find out how many different breath specimens should be used if we want to estimate the long run proportion of correct identifying for a dog with a margin of error that is 0.1 and a confidence level of 95%. Okay, since this has never been done, this is like brand new stuff. I'm going to first of all put our formula down. V star over m squared. We have no p's to work with. So this is brand new. So there's no p hat to work with from the history. So that means we're going to let p hat equal 0.5 will be used. And so now we're going to have that 0.5 times my 1 minus 0.5. We need our z star for our 95% confidence level. That is 1.96. Again, that's from my table that we had quite a while ago. The margin of error is 0.10. That we're going to be squaring. 1 minus 0.5 is 0.5. Okay. Again, we're going to the calculator, taking 1.96 divided by my 0.1, first of all, squaring that number, times 0.5 times 0.5, and we come up with 96.04. So again, this is an n. N is a sample size, which has to be a whole number, and we always round up when estimating our sample size, because we want to make sure that we get the accuracy that we need. And if we didn't, we might not quite get our margin of error that we want or that confidence level that we wanted. Okay, so there is how we can find our n values when we're talking about proportions. So kind of to recap this little unit, we've learned how to do some probabilities for our samples. So like X bar, We also learned how to find probabilities for some proportions, very similar, but a little different than what we've seen in the past. Then we talked about how to find confidence intervals for the mean or a confidence interval for a proportion. And lastly, if we were starting from scratch, to find the sample size needed to get to a certain result if we were then going to be taking and finding a confidence interval. So in like this one, we'd want to go and talk to get 97 people to breathe on this dog. And then we could find, we'd want to make sure to have some that had cancer, known cancer, and some that didn't, so we could find out how accurate this dog would be. So that would be the thing we'd need in this situation, is we'd have people with cancer versus and people without cancer, knowing those things to find out how accurate our dog was. So that is what we've kind of done in this unit. This also concludes this video. So hopefully you're doing well as you're progressing through the course. I look forward to seeing you again, except I don't actually see you, but I hope that these videos are helping. And I look forward to you seeing you in the next video, and to have a wonderful day.